Okay, so in the previous lecture, I had asked you to do these three problems, right? Do these three problems. So let us check the answers of these three problems. So in this case, del f by del x is 1 over x times 1 over x plus 2y plus 3z times the differentiation of this equation inside, sorry, this function inside with respect to x, which gives you 1. Del f over del y is the differentiation of this complete thing, which is 1 over x plus 2y plus 3z, and differentiation of the function inside with respect to y, which gives you 2. Similarly, del f by del z is equals to 3 over x plus 2y plus 3z. Clear? Okay, the next problem is this one. So differentiating this function with respect to x will give you minus half times this function to the power minus half minus 1, which is minus 3 by 2, times differentiation of the function inside with respect to x, right? So answer is minus x over x square plus y square plus z square. You can obviously see that this function is kind of symmetric, so the differentiation with respect to y and the differentiation with respect to z will come out to be same, just replacing x with y and z. Is it clear? The third problem was maybe a bit difficult for some of you, because you were given hyperbolic sine xy minus z square. Okay, what the concept is that, I guess you people know this, sine hyperbolic of x is basically e to the power x minus e to the power minus x by 2. Okay, so simply using this substitution, so sine of h becomes e to the power xy minus z square minus e to the power z square minus xy over 2. Now you need to differentiate this with respect to x, with respect to y, and with respect to z, as stated in the previous lecture. Okay, got it? Okay, one more thing. Also, you should remember cos h of x is given as e to the power x plus e to the power minus x by 2. Is it clear? So according to the answer you get for fx, fy, for fx, fy, and fz, you can convert your answer to cos hyperbolic values. Okay, clear? Now we are talking about continuity and partial derivatives. So how is continuity and partial derivatives might be related? Let's see. So if a function fxy is continuous at a point P, the partial derivatives fx and fy at P may or may not exist. Okay. So what they are telling is that, see, in case of single variable functions y is equals to fx, we knew that if this function is differentiable at x equals to a, the function must be continuous at x equals to a, but the converse might not be true. A function may be continuous at x equal to a but may not be differentiable at x equals to a, while the function, if differentiable at x equals to a, will be continuous at x equal to a. Is it clear? Let's check this particular problem. So if fxy as x plus y times sine of 1 over x plus y, but x plus y is not equals to 0, and if x plus y equals to 0, the value of the function is 0. Okay, now first what we need to check, whether this function is continuous at x equals to, whether this function is continuous at xy equals to 0 comma 0 or not. See, at xy equals to 0 comma 0, you will get xy equals to 0, right? I'm just stating it. The reason I'm doing this, because so f of 0 0 will be 0 according to the definition of the function, right? So what we need to check is that limit xy tends to 0 0, fxy needs to be f of 0 comma 0. Is it clear? Okay, so let's check the limit of this particular function. So we kind of assume that the limit of this function is 0, so that we can check whether this equality holds or not. Is it clear? So mod of x plus y times sine of x plus y minus 0, if less than epsilon, we are doing the scratch work here. Okay, we are doing the scratch work here. If this is minus 0 less than epsilon, then we can divide the modulus, because mod of ab equals mod a into mod b. So mod of x plus y times mod of sine of x plus y less than epsilon. Now mod of sine functions are less than 1, so we can replace this with mod of x plus y is less than epsilon. Okay, also we know mod of x plus y is less than equals to mod of x plus mod y, so we replace mod of x plus y with mod x plus mod y, which is further less than epsilon. Now we can replace mod x with delta and mod y with delta, because we need to show that mod x less than delta and mod y less than delta implies that the value of the function less than epsilon. Since we are doing the back calculation, so we will take the greater sides, right? So putting mod of x equals to delta and mod of y equals to delta, we can obviously say that 2 delta must be less than epsilon. Clear? So delta must be epsilon less than epsilon by 2. Okay, Now we can come to our proper proof. Here I have taken 2 delta equals to epsilon. This will also do, because if 2 delta is less than epsilon, then something less than 2 delta will automatically imply it is less than epsilon 2. Also you can take delta is less than epsilon by 2, because then also something less than 2 delta will automatically imply it is less than epsilon. You can do anything. So we choose that. So I have just done the solution very shortly, and so I'm giving you the explanation. So we choose that for all delta greater than 0 there exist, so for epsilon greater than 0 there exist delta greater than 0 such that delta is less than epsilon by 2. Now mod of x is less than delta, mod of y is less than delta implies mod of x plus mod of y is less than 2 delta, which implies mod of x plus y is less than 2 delta. Reason is mod of x plus y is less than equals to mod of x plus mod of y, which is further less than 2 delta. Is it clear? So mod of x plus y less than 2 delta. Now since mod of sine of 1 over x plus y is less than 1, less than equals to 1 rather, so we can just multiply it here. So mod of x plus y times mod of sine of 1 over x plus y is less than 2 delta, which implies mod of x plus y times sine of 1 over x plus y minus 0 is less than 2 delta, and delta is less than epsilon over 2, so this is automatically less than epsilon. Hence the limit of the function as it approaches to 0, 0 comma sorry, as xy approaches to 0 comma 0, x plus y into sine of 1 over x plus y is equals to 0, which is equals to f of 0 over 0. So the function is continuous at xy equals to 0 comma 0, right? The function is f is continuous at x equals to 0 comma 0. Is it clear? Okay. Now let us check whether fx and fy exist or not. So we know fx is given as limit h tends to 0 f of x plus h comma 0 minus f of x comma y, sorry, not 0. Let me just give you the general explanation. So general explanation, fx is given as limit h tends to 0 f of x plus h comma y minus f of xy over h. Here you have x equals to 0, y equals to 0, because you are finding the derivative at 0 comma 0. So limit h tends to 0 f of 0 plus h comma 0 minus f of 0 comma 0 over h. So this is h times sine of 1 by h minus 0, which is limit h tends to 0 sine of 1 by h, and we know that this particular limit does not exist. Clear? So fx does not exist at, so fx does not exist at 0 comma 0, but function is continuous at 0. Is it clear? Is it clear? Okay. Let's check the next problem. So you have a function given fxy is equals to x square y over x to the power 4 plus y to the plus y square, and you are asked to show that this function is discontinuous at xy equals to 0 comma 0, but fx and fy exist at 0 comma 0. Okay, so let's see. Now see, this type of problem we have already done, right? If you take fxy is equals to x square over y, x square times y over x to the power 4 plus y square, and you need to find limit, and you need to check whether limit xy tends to 0 comma 0 fxy exists or not. So if you try to take the path along y is equals to mx square, right? Y equals to mx square. Origin falls on this particular path, therefore we can make xy reach the origin using this particular path. So if we take this particular path, so limit x tends to 0 equal tends to implies limit y tends to 0, we can use limit x tends to 0 only. Put y equals to mx square in the given function. So you have x square times m times x square over x to the power 4 plus m square x to the power 4, which is equals to limit x tends to 0 x to the power 4 times m over x to the power 4 times 1 plus m square. So x to the power 4 and x to the power 4 cancels out since x is not equals to 0. So the value comes out to be m over 1 plus m square. That implies that the limit is path dependent, and if the limit is path dependent, then the limit does not exist. So we can obviously say that this limit xy tends to 0 comma 0 does not exist. What is the value of fx at origin. So it is limit h tends to 0, f of 0 plus h comma 0 minus f of 0 comma 0 over h. Now if at 0 plus h comma 0 of this function, so 0 plus h, so we put 0 plus h in place of x and 0 in place of y. Putting 0 in place of y, we will get the value of this function to be 0. Similarly at origin also, the value of this function will be 0 because it is already given here, right? So 0 minus 0 over h, as h tends to 0, will basically be equal to 0. Therefore fx exists at the value of fx is 0. In the exact similar way, fy will also exist. Clear? So fx and fy exist, but limit at that particular point, that is origin, does not exist. Is it clear? Result. This is a very important result about continuity and partial derivatives. So if the partial derivative fx and fy of fxy exist and are continuous throughout a disk centered at AB, then f is continuous at AB. Is it clear? So how can we imply continuity with partial derivatives? Is that if you have a function f, so its partial derivative with respect to x is fx and its partial derivative with respect to y is fy. If fx and fy exist and both of them are continuous throughout a disk centered at AB, so this is the point at which you need to find the continuity. So you form a disk around that particular point, centered at that particular point, and fx and fy they exist and are continuous throughout this region, then we can say that the function f is continuous at AB. Is it clear? Got it? The concept is clear? I mean the statement is clear? Okay. Now we need to check what are second partial derivatives. Okay. What are second partial derivatives? So first let us recall about single variable functions. So suppose you have a function y is equals to fx. So you had dy equals to dx, which was given as y1. It was equals to f dash x. That is differentiation of f one time with respect to x. What was d2y by dx square? It was given as y2. It is differentiating f twice with respect to x. Differentiating x twice with respect to x, nothing else. Or differentiating the first derivative. This is called the first derivative, right? This is called the first derivative. Differentiating the first derivative with respect to x gives you the second derivative. A similar, the same explanation is given here as well. So fx is the first partial derivative with respect to x, which is given by this particular value. If you differentiate the first partial derivative with respect to x again, if you differentiate the first partial derivative with respect to x again, then what you get? You get the second partial derivative with respect to x, and it is denoted by f of xx. Clear? Got it? Clear? Your fx is given as limit h tends to 0 f of x plus h wait. So your fx is given as limit h tends to 0 f of x plus h comma y minus f of xy divided by h. So your f of xx is differentiating fx with respect to x. So fx x plus h comma y minus f of xy, fx of xy by h. Clear? Clear? Differentiating the first partial derivative with respect to differentiating the first partial derivative with respect to x itself. Okay, this will give you the second partial derivative. Similarly, del 2f by del y square is also the second partial derivative with respect to y. Is it clear? Now, in this case, we can also find second partial derivative with respect to different variables. That is, if you differentiate fx with respect to y, if you differentiate fx with respect to y, you get del 2f over del y del x. This is the notation. This is the notation which is given as f of xy. F of xy is partially differentiating fx with respect to y. Similarly, partially differentiating fy with respect to x will give you the value f of yx. Is it clear? Very simple explanations. Suppose you are given this function f is equals to 2x minus 3y whole cube. You are asked to find fx, fy, fxx, fxy, fyx, fyy. Okay, let's check. So what is fx? Fx is 3 times 2x minus 3y whole square times 2. That is 6 times this. Clear? What is fy? It is, so 3 times 2x minus 3y whole square times minus 3, because we need to differentiate inside with respect to y. So it is minus 9 times 2x minus 3y whole square. Is it clear? Now fxx. Fxx is differentiating fx with respect to x. So differentiating this with respect to x, you get 2 times 2x minus 3y whole square times 2, right? 6c. This is 6 times 2 times 2x minus 3y times differentiation of inside with respect to x will give you 2. That is 24 2x minus 3y. Similarly, if yy is basically equals to minus 9 into 2 into 2x minus 3y into minus 3. Fxy is differentiating fx with respect to y. So differentiate this with respect to y will give you 6 times 2 times 2x minus 3y times minus 3. Differentiating inside with respect to y. And f of y is differentiating y with fy with respect to x. This is minus 9 times 2 times 2x minus 3y times. Clear? Got it? So these are the values of fx, fy, fxx, fyy, fxy and fyx. Clear? Second partial derivatives and first partial derivatives are clear at this moment. So here you have one more problem. You are given this function f equals to x over x square plus y square, where xy is not equals to 0. You need to find fx, fy, fxx, fyy, fxy and fyx. This is a homework. Okay, you can do it on your own. Let us check the next problem. So here you are given fxyz, f of function f of xyz is equals to x to the power x, y to the power y, z to the power z. You need to find the values of fx, fy, fz, fxx, fyy, fzz, fxy, fxz, fyx, fyz, fzx, fzy. All these derivatives you need to find. Okay. Acha, to solve this particular problem, I'm just giving you a simple hint and you can do the rest of the problem yourself. Hint is, if you are given a function y equals to xx, then dy over dx is given as x to the power x into 1 plus ln x. Okay. You can use this particular concept to solve this problem. You can do it on your own. You can do it on your own. Okay. You can check all the derivatives possible. Okay. Now here's a very good problem. fxyz is e to the power 3x plus 4y cos of 5z, and you need to prove fxx plus fyy plus fzz is equals to 0. Let's see. So first partial derivative with respect to x is 3 times e to the power 3x plus 4y times cos of 5z, because everything except x is constant. F of xx is therefore 9 times e to the power 3x plus 4y times cos of 5z. You can do it on your own, and the derivatives on your own. E to the power ax, if you differentiate this with respect to x, you get a times e to the power ax. This is the concept used here. Okay. Similarly, f of y is 4 times e to the power 3x plus 4y times cos of 5z. So if yy is equals to 16 times, because 4 gets multiplied again, so 16 times e to the power 3x plus 4y times cos of 5z. F of z is derivative of cos is minus sign, so 5 will also get multiplied because we need to differentiate the inside as well with respect to z. So f of z is minus 5 times e to the power 3x plus 4y times cos of 5z. F of z is minus will remain, right, because derivative of sign is cos. So minus 25 times e to the power 3x plus 4y times cos of 5z. So therefore fxx plus fyy plus fzz equals 9 times e to the power 3x plus 4y cos of 5z plus 16 times e to the power 3x plus 4y cos of 5z minus 25 times e to the power 3x plus 4y cos of 5z, which is equals to 0. Clear? Clear? Similarly, let's check the next problem. So you are given a function here fxy. So xy is equals to x square minus y square by x square plus y square. Okay. Suppose you are asked to check whether, let me check it. So they are asked to check whether fxy equals fyx or not. Whether fxy equals f of yx or not. Clear? This is what you are asked to check. So what is fx here? So we will use the first principle. It will make the problem a bit easier, right? Using first principle, you can see f of xy at 0 comma 0 equals limit h tends to 0 f of 0 plus h comma 0 minus f of 0 comma 0 over h. So putting y equals to 0 here, the numerator becomes 0 and this is also 0. So f of, sorry, this is not xy, this is fx. So its value is 0, right? At 0 comma 0. Clear? At 0 comma 0. Got it? Clear? We drink some water. Similarly, you can do it for fy as well. So this is limit h tends to 0 f of 0 comma 0 plus h minus f of 0 comma 0 divided by h. Okay, check what it will come out to be. It will come out to be 0 as well. Got it? Got it. Now it's your homework to find out the values of fxy and the values of fyx and to check whether xy equals xy equals fyx or not. If equals, then okay. If does not equal, then also it's okay. You can check it on your own. So my answer tells that fxy will eventually come out to be fxy will not be equals to f of yx. Okay, so you can verify whether it happens or not. Okay. Next we come to the last topic of our lecture, which is Euler's theorem. So Euler's theorem says that if fxy and its partial derivatives fx, fy, fxy and fyx are defined throughout an open region containing a point AB and all are continuous at AB, then fxy at AB equals f of yx at AB. Is it clear? So fx, fy, fxy, fyx, all these values exists in an open region which has the point AB. Open region, remember, contains all its interior points. And each of these values are continuous at the given point AB. Then the second partial derivative of x with respect to y at that point will be equal to the second partial derivative of fy with respect to x at that particular point. Okay, so fxy equals fyx. This is not a general equality. Okay, this won't happen always. This will happen only if fx, fy, fxy and fyx exist in open region which contains the point AB and fx, fy, fxy and fyx are continuous at the point AB. Only then this equality will hold. Is it clear? So let this lecture be up to this much, guys. In the next lecture we will be coming with some more concepts on multivariable calculus. Meet you guys in the next lecture.